The formation of the earliest and lightest elements occurred during a process called Big Bang nucleosynthesis, which took place in the first few minutes, say around 3 to 20 minutes after the Big Bang. Now let's talk about how it all unfolded.
In the first few seconds during the quark epoch, the universe was said to be filled with dense, hot quark-gluon plasma, which contained quarks, leptons, as well as their antiparticles. These particles predominantly comes from rare, high-momentum collision between quarks and gluons that occur in the hot early stage of the reaction, forming mesons or baryons. And so as the universe rapidly expanded, it cooled down to temperatures that allows from quarks to combine, therefore forming protons and neutrons.
As the less than 3 minute mark after the Big Bang occurred, form hydrogen and deuterium. As the temperature dropped down further, proton, mainly hydrogen, nuclei, and neutron, began to fuse to form deuterium, which, however, deuterium formation was delayed until the universe cooled down to around 1 billion degrees Kelvin to be able to allow these particles to stick together without being torn apart by high-energy proton.
Once deuterium became stable enough, it acted as building blocks for further nuclear reactions. Deuterium nuclei fused to form helium-4 that consisted of 2 protons and 2 neutrons, small amounts of helium-3 that consisted of 2 protons and 1 neutron, as well as tritium, which consisted of 1 proton and 2 neutrons, and lastly, lithium-7, which had 3 protons and 4 neutrons. The vast majority of the nucleosynthesis formed helium-4, therefore making it the second most abundant element in the universe after hydrogen. At the end of nucleosynthesis, which was approximately 20 minutes after, the temperature and density of the universe dropped so low, disabling nuclear fusion. As a result, no heavier elements beyond lithium could form. This left the universe to be composed of 75% hydrogen and 25% of helium, with some trace amounts of deuterium, helium-3, lithium, and beryllium. These elements, mainly hydrogen and helium, provided the universe raw materials for the formation of all the stars, galaxy, and every later cosmic structure. Heavier elements would only then form billions of years later through stellar nucleosynthesis inside stars.
Which brings us to our next topic, stellar nucleosynthesis. The process depends on the mass of the star and progresses through different stages as the star evolves. Let's all tackle how it works.
First and foremost, let's talk about hydrogen fusion of main sequence stars. In most stars in the universe, the main fusion process occurs in their cores, which allows protons, primarily hydrogen nuclei, to overcome their mutual electrostatic repulsion and fuse together. This stage is known as the proton-to-proton chain reaction that are found in smaller stars like the Sun or the CNO cycle that occurs in larger stars, by which stars convert hydrogen to helium.
Next, we have the helium fusion found in red giants. As stars exhaust their hydrogen supply into the core, gravity then causes the core to contract and it half. When the temperature reaches about 100 million degrees Kelvin, helium fusion begins a process called the triple alpha process. Through the reactions in the triple alpha tree, helium-4 nuclei or alpha particles fuse to form carbon-12, which is the most abundant isotope for carbon. As the core further contracts and heats up,
Now we move to the fusion of heavier elements in massive stars. In massive stars that are several times the mass of our Sun, once helium is depleted, the core continues to contract and heat up, which in turn allows for the fusion of progressively heavier elements. The sequence of fusion stages typically follows the order starting from carbon fusion, which is when the core temperature exceeds about 600 million degrees Kelvin. carbon nuclei begin to fuse in order to form elements like neon, sodium, and magnesium. Finally, at core temperatures exceeding 2 billion degrees Kelvin, silicon nuclei fuse to form iron.
The role that we reach the iron limit. Iron is unique in the sense that it has the most efficiently bound nucleus, as it has the least average mass per nucleon of any other element. Fusion of iron or heavier elements does not release energy but rather it requires energy. This is because the blinding energy per nucleon is at its peak in iron. Therefore, when a star's core accumulates a significant amount of iron, fusion halts and the star can no longer sustain its pressure outward against gravity.
Let's now talk about supernova explosions, where elements that are heavier than iron are formed through the process known as neutron capture, primarily from the so-called R process, also known as rapid neutron capture process. How does it unfold during a supernova, you may ask? First, we go through the iron core collapse, where in the final stages of a massive star's life, the core is mainly composed of iron, in which it cannot undergo fusion in order to release energy. When a core reaches a critical mass, it then collapses under its own gravity, leading to a sudden increase in both temperature and pressure.
We then go through the core collapse. This process happens incredibly fast, where the star compresses the core to extremely high the sides. Therefore, the outer layer of the star fall inward, triggering an immense explosions. We call a core collapse supernova. During the core collapse, a largest number of neutrons are generated as protons and electrons are forced together due to the intense pressure. They combine to form neutrons in a process we call neutralization. This therefore creates an environment that is rich in neutrons. These neutrons are essential for process as they rapidly collide with atomic nuclei.
So, how does the R process work anyway? In the R process, atomic nuclei, mostly iron and other light elements present, before the explosion rapidly capture neutrons. The very high neutron flux in a supernova usually means that atomic nuclei can absorb multiple neutrons in a very short period of time. We're talking like fractions of a second. And as a nucleus captures a neutron, it becomes an unstable isotope. These neutron-rich isotopes then undergo a process called beta decay, where a neutron transforms into a proton, which emits an electron and an antineutrino. This turns the nucleus into a heavier element with a higher atomic number. The cycle of rapid neutron capture and beta decay allows the creation of elements heavier than iron. For example, gold, platinum, uranium, and thorium. Through a supernova explosion, newly formed elements can be ejected into space, where they become part of the interstellar medium. With time, these materials are turned into new stars, planets, and even other celestial bodies throughout our universe.
During ancient Greek philosophy, approximately 5th century BCE, the theory of the atom started from Leucippus and Democritus. Greek philosophers from around 450 BCE, they proposed that all matter was made up of small, invisible particles called atoms, which meant invisible. According to them, atoms were eternal, unchangeable, and varied in shape and size, moving through a void.
Aristotle, on the other hand, opposed this theory during the 4th century. Aristotle rejected the idea of atoms in the void, but instead theorized of matter based on 4 fundamental elements. These elements were earth, water, air, and fire. His views were dominant for over 1,000 years, largely delaying the development of atomic theory, but gave way to evolution in alchemy. His theory of matter therefore was more of a philosophical approach, prioritizing form and substance rather than physicality.
John Dalton's atomic theory in 1803 is often known for the modern scientific revival of the atomic theory. He proposed that each chemical element is composed of atoms of a single, unique type and that these atoms combine in simple ratios to form various different compounds. His theory explained that the law of conservation of mass and the law of definite proportions. Through his theory, he suggested that matter consists of indivisible atoms. Atoms of a given element are identical in mass and properties, and lastly, atoms combine in whole number ratios to form different compounds. John Dalton is also to of an atomic model, which is often referred to as the bowling ball model, as he defined an atom to be a ball-like structure mainly due to the electron and nucleus being unknown at this time.
A.J. Thomson discovered the electron in 1897, therefore proving that atoms were divisible and contained smaller particles. He proposed the plum pudding model of the atom, where electrons were scattered within a positively charged soup.
Ernest Rutherford in 1911 conducted the gold foil experiment, which later led to the discovery of the nucleus of an atom. He showed that the atom consists of a tiny, dense, positively charged nucleus surrounded by electrons. This then overturned Thomson's model.
Niels Bohr introduced the concept of quantized orbits for electrons in atoms in the year 1913. He proposed the idea that electrons orbit the nucleus in fixed energy levels, and that energy is absorbed or emitted as electrons move between these levels, which then explained atomic spectrum.
The quantum mechanical model describes atoms in terms of probability and wave function, with electrons occupying different regions around the nucleus rather than fixed orbits. It incorporates both the particles and wave-like behavior of electrons.
Werner Heisenberg and Erwin Schrödinger during the 1920s showed the development of quantum mechanics, which gave us a new understanding of the atom. Heisenberg's uncertainty principle and Schrödinger's wave equation led to the modern view that electrons do not orbit the nucleus in fixed paths but exist in regions of probability that are known as orbitals.
Despite the discovery of protons, neutrons, and electrons, it was not the end of the story, as in the mid-20th century, particle physicists discovered that protons and neutrons are made up of even smaller particles, known as quarks, which are bounded together by the strong force, mediated by particles that were called gluons. This is part of the Standard Model of particle physics, which describes the fundamental particles and forces in the universe. The discovery of the Higgs boson in 2012 at CERN's Large Hadron Collider confirmed the existence of the Higgs field, which gives particles mass and is a cornerstone of the Standard Model.